Hi everyone. So I'm going to be out for a little bit longer, but I wanted to make a video lesson for 4.2 because it starts getting a little bit more complicated. So I wanted to show you guys how to do it, not just from the notes because it's a little hard to follow. If you didn't get 4.1 notes, we're going to cover that a little bit in some of these examples that we're doing for 4.2. So hopefully that will kind of refresh our understanding of 4.1. So for 4.2, we're talking about concavity and inflection points, which is going to be mainly using the second derivative. So we're using second derivative here so that we can get the concavity and inflection points. And that's going to help us determine a couple things. If we have an upward concavity or a downward concavity here. Okay, upward or downward. We can also find what we call points of inflection or inflection points using the second derivative. In the first derivative, we called there were similar type of points called critical numbers, which I will again cover in this video, but we're mainly going to focus on the second derivative here. So what it looks like in the graph visually when we do open upward concavities and downward concavities is it'll look like this. It'll look like an upward, which looks like a cup, up like a cup, or it'll be a downward concavity, down like a frown. So the cave or the indent is opening down or it's opening up depending on it. How I remembered it was this looks like a U for up and this looks like an N for down. Okay, but that's how I do it. Up like a cup is pretty good. Down like a frown is pretty good too. So whichever way you guys prefer. Like I said before, we're using the second derivative. So we will do everything with our second derivative, and we'll do our sign chart just like we did in the previous lesson. So you'll see what I mean by a sign chart if you didn't understand from the first lesson. Okay, mainly what we're looking at is if our second derivative is positive or negative. If it is a positive second derivative, then we have an upward concavity. If we have a negative second derivative, then we have a downward concavity. So again, upward concavity is up like a cup. Downward concavity is down like a frown. So let's go into our example problem. We want to determine the open intervals in which the graph of f of x, 4x to the power 4 minus 9x cubed plus 5x minus 1 is concave up or down. So we will do this with a sign chart for the second derivative. So let's first find our derivatives. We're going to do f prime and then f double prime. So f prime is going to get us 16x cubed minus 27x squared plus 5. The derivative of that would be the second derivative, which would get us 48x squared minus 54x. So once we have our second derivative, we are going to set our second derivative equal to 0 and solve for x. All right, so let's put that in. We are going to get 0 equals 48x squared minus 54x. And I'm going to take out a GCF, factor out a GCF, and see what I can do here. 0 equals, GCF here looks like 6x. So I'm going to take out a 6x from both of those terms. And what I'm left with is 8x minus 9. All right, so we have our two factors. We're going to set each of these factors equal to 0. And we're going to solve for our two x values. So 6x equals 0. And 8x minus 9 equals 0. X will equal 0, and x will equal 9 over 8. And these are our 2 points we're going to put on our sign chart for our second derivative, and we're going to test our values to see which intervals are positive and negative. So I'm going to set that sign chart over here. This is going to represent f double prime. And I'm going to plot the 2 points that I have found in the previous part. So I'm going to plot 0, and I'm going to plot 9/8. So at this point, we want to figure out what is happening between these points. We want to see if it's a positive or negative second derivative to determine the concavity of the original function. So what we can test in each of these is going to be a little bit different. We're going to test 3 different values. For the first interval here, we're going to test something less than 0. So we're just going to test -1. So f double prime of -1. In the middle section, we can test f double prime of +1. And then even for the last section, we can go a little crazy here. We don't have to do like 2 or 1. Let's try like 400 because the value doesn't really matter. We're really looking at if it's a positive or negative value when we plug it in. So you can plug it into 2 different spots, and it doesn't really matter which one you do. You can plug it into this original f double prime, or you can plug it into the factored out version of it. Some might find it easier to plug it into the second one, just because it's easier to see what values it'll be, if it'll be a positive or negative, and how the positive and negative interact. But it is totally fine to do it in this original f double prime. So I'm going to plug in f double prime into I'm going to plug in -1 into the second derivative function. I'm going to plug it into here. So when I plug in -1, the -1 gets squared, so it's positive, and then -1 times this -54 gives me a positive. So that will be a positive number plus a positive number, meaning it's positive. So if you notice, I'm not finding the values. I don't really care about the values. I just care when I plug in the value if I'll have a negative or positive answer. So if you can do this mental math in your head, it speeds up the process. If not, just use a calculator, calculate the value, and just figure out if it's a positive or negative value. Okay, so I'm going to plug in 1 into my function, and I'm going to see that I get a negative answer. Okay, so if you don't understand how I'm doing this, pause the video and see how I got this negative answer without having to actually plug it in. Okay? Now, last value, 400, I plug in 400 because it's any number after 9/8. So plugging in 400, 400 squared is a huge number, and it's a positive number, so it really doesn't matter that this is going to be negative, because this number, when I plug in that 400, is going to be so massive, it makes this a marginal change. It's very small. So it's going to be a positive number when I plug in 400. So put those values into my chart, and let's see what happens. I have the first interval as a positive interval, changing into a negative interval, and then changing back into a positive interval. What we just found was that our second derivative is positive in this first interval, so that means it's an upward concavity, so it'll look like that. It'll bend up like a U. In the middle, we'll have a downward concavity, frown, down like a frown, and then again up like a cup. So that's how the graph will look at those basic points. So conclusion, we know where the graph is concave up and concave down. Okay. F of x, the original graph, is concave up at 2 intervals, right? It's at the interval -infinity to 0 and 9/8 to infinity. We'll put that U as a union. Second conclusion that we know is that the original f of x function is concave down at the interval 0 to 9/8. And again, all of these intervals are with parentheses, not brackets, because at those exact points, our second derivative is 0. It is not positive nor negative, it is 0. So when I talk about my concave up or down, our intervals have to be in parentheses, not brackets. Right. Last thing I want to talk about here, we're going to talk about these points of inflections. Now we already did find our points of inflections from our previous problem. These zeros are where our points of inflections are going to be. Now the point of inflection only happens where the concavity changes. And that is what we call the point of inflection or inflection points. So if, let's say, 0 had positive concavities on both sides of it, then 0 would not be a point of inflection. But in this case, in our actual example, since we have a change in concavity on both sides of this point, 0 is going to be an inflection point. 9/8 will also be a point of inflection because there's a change in concavity. It goes from negative to positive. So it only happens when the concavity changes between that point. Okay. So we do have 2 points of inflections in our previous example. So what we're going to do to find the actual point is we're going to use f of x. We're not going to use that second derivative function anymore. We're going to plug in our values, those x values, into our original function. So our original function is up here. I'm going to copy that down right here. Oops. And this is the function we are using. We're using the original f of x function, and we're plugging in x equals 0 and x equals 9/8. Now you can use a calculator to do this. I've already done it, but see if you can do it as well with your calculator. But you should get f of 0 equals 1, and f of 9/8 gets you negative 1.78. So those are our y values of our inflection points. So just to summarize, make sure you use f of x to find the y values of these inflection points. Okay. So our 2 inflection points are at 0, 1, and at 9/8, negative 1.78.